In this lesson on integrals of vector functions, we're going to look at projectile motion. Let's start with the vector and parametric equations for ideal projectile motion. In this example, we have a projectile that is shot upward. It has an initial velocity of v naught, and this is at time equals 0. So when this happens, its horizontal velocity component, v in the I direction, is the absolute value of the initial velocity times the cosine of the angle formed from the horizontal. And the vertical upward velocity, v in the j direction, is the absolute value of the initial velocity times the sine of the angle formed with the projectile in the horizontal. And then we also have a gravity which is pulling our projectile down due to acceleration, and the acceleration is in the j direction, and the acceleration is a negative, it's gravity, and it is going downwards. So let's take this and move this up. Okay, so we want to start with our velocity equation, and we know that our velocity is going to be equal to our initial velocity, v naught, plus our velocity that's due to acceleration. So what we want to do is we want to find the velocity due to acceleration, and we know that acceleration is equal to the change in velocity with respect to time, which means that we can rewrite this as our little bit of change in velocity is equal to our acceleration, which is negative g, times our little bit of change in time. So what we want to do here is we want to integrate both sides. So let's move this up, and I'm going to move down here, and let's start this integral. So I'm actually going to work out this integral right here. And this is in our j direction. Remember, the acceleration due to gravity is in the j direction, and we figure out this component, we'll put that in. And so we have, let's move this over just a tiny bit here. We have that this integral right here is equal to negative gravity times time plus our constant. Okay, so what we want to do is go back and we take a look at our velocity equation. It has an initial velocity and then the velocity due to acceleration. The initial velocity has two components. It has a component in the I direction and a component in the j direction. And then our acceleration component, the velocity due to acceleration, which is right here, that's also in the j direction. So let's go ahead and write out our velocity equation in its component form. So we have our velocity initial, v naught, in the I direction is the absolute value of v naught times the cosine of alpha, and that's in the I direction, plus the absolute value of the velocity, v naught, times the sine of alpha, and that is in the j direction, minus the acceleration due to gravity, which is gt in the j direction. So let's move this up. Okay, now we want to look at the relationship between velocity and our location. And we know that the velocity is our change in distance, r, with respect to time, So from this, we can say that a little bit of change in distance is equal to our velocity times a little bit of change in time. And if we integrate both sides, this will tell us what our equation for distance is. So we're going to take this equation right here for velocity, and we are going to put it down here, and we're going to integrate it with respect to time to find our equation for distance. So let's take this and move it up and get my pencil back. We're going to say that our equation for distance is equal to the integral of the absolute value of our initial velocity times the cosine of alpha in the I direction plus the absolute value of our initial velocity times the sine of alpha in the j direction minus gravity times t in the j direction, and this will all be integrated with respect to time. So I'm going to take this and move this up, and let's do our integration. So r is equal to, and if we look at our first term here in our integrand, the absolute value of the velocity and the cosine of alpha are considered constants. There's no t in here, okay? And matter of fact, let's just fix this ending here. This is with respect to t, of course. And so what we want to do here is we would say that the equation for our distance is the absolute value of the velocity times the cosine of our angle alpha times t, that's coming out of the integration in the I direction, plus the absolute value of the initial velocity times the sine of alpha times t, and that's in the j direction, minus, now g is a constant, but the antiderivative of t is t squared over 2, so we'll put t here, 2 here, and this is a 1/2, and that's in the j direction. Now we can simplify this and put it in its totally in its component form. In our I direction, we have v naught times the cosine of alpha times time. That's in the I direction. And then in the j direction, we have the absolute value of v naught times the sine of alpha times time minus 1/2 times gravity times time squared, and that is in the j direction. And here we have our final equation for ideal projectile motion. In this example, we're going to look at a projectile that is fired from the origin over horizontal ground at an initial speed of 500 meters per second. It is launched at an angle of 60 degrees. The question is, where will the projectile be in 10 seconds? So let's draw a picture. So here's our horizontal ground. We launch our projectile at an angle of 60 degrees and an initial velocity of 500 meters per second. And our projectile is going to go like this, and we want to know how far until, boom, it hits the ground. So we want to look at what is this distance, r, that it travels, r final, I guess we could say, call it r final. And we must keep in mind, let's see that we have a horizontal velocity, we have a vertical velocity upward, and then we have gravity that's pulling it down. So a negative g pulls it down. Let's take this and let's move this diagram up here to the right. And let's start working out our math for this. Our equation for location, distance, from our previous slide is the initial velocity v naught times the cosine of the angle formed with the horizon, alpha, times time, and that's in the I direction, plus the absolute value of our initial velocity times the sine of that angle alpha, and that's times t, minus 1/2 gravity times time squared, and that is in the j direction. So let's take that, we'll move that up. That's our equation for our location, our distance. So that means that r is equal to, well, the absolute value of our initial velocity is 500 meters, times the cosine of our angle, 60 degrees, times time. Well, time is 10 seconds, and that's in the I direction, plus, then we have, again, v naught. Our initial velocity is 500 meters per second, times the sine of the angle 60, times a time of 10 seconds, minus 1/2, and our gravity is 9.8 meters per second squared, and our time is 10 seconds, and we square that, and that's in the g direction. So let's move that up, and let's figure this out. So our distance is equal to 500 times the cosine of 60, which is 1/2, times 10, and that's in the I direction, plus 500, and the sine of 60 is the square root of 3/2, and then times 10, minus 1/2 times 9.8 times 100, and that's in the j direction. Let's cancel some of this out. Let's see, this 2 cancels out this 10, leaving it as a 5. 2 divided by 10 is a 5. And then let's take this and let's move this out and finish this off. Okay, so what we get is that our location, r, is equal to 5. We have 5 times 10 is 5,000. 1/2 of 5,000 is 2,500. So we have 2,500 meters in the I direction plus, and we're going to work this out, and this becomes, let's see, 2,500 times the square root of 3 minus 490, and that's how many meters in the j direction. We can move that up. And let's move that up. Those two separated. And this expression right here gives us our horizontal and vertical distance after 10 seconds of our projectile.